So in this video we're going to implicitly find a partial derivative. And so these are the formulas that we developed 2 videos ago, and what we want to do is take advantage of them to easily find a partial derivative. So right here I want to find partial z partial x. So we're being asked to find partial z partial x, and we have a function x squared y squared minus x squared z squared plus 3z squared plus 4xy equals 10. And the way this is going to play out is similar to how we played it out in the previous video. So we're going to take and subtract that 10 off of both sides. So we're going to do x squared y squared minus x squared z squared plus the 3z squared plus 4xy, and then we're going to subtract that 10 off of both sides and get it equal to 0. And then we're going to let this piece here be our f of x, y, z. So we let f of x, y, z equal the x squared y squared minus x squared z squared plus 3z squared plus 4xy minus the 10, and clearly because this mess here is equal to 0, that means that f of x, y, z is equal to 0, which is what we need. And because the formula that we developed depended on our function being equal to 0, which made the rate of change 0 in the function that we were working with. And so once I get my function of 3 variables, I just say which derivative do I want? I want partial z partial x. So I'm going to take partial z partial x and find it by doing the opposite of the partial derivative with respect to x of my function divided by the partial derivative with respect to z of my function. So first we calculate f sub x, the partial derivative with respect to x. So just walk through piece by piece. The derivative of x squared y squared is going to be 2x y squared, because y squared is a constant. It's just going to stay as part of that constant coefficient on x, minus 2x z squared. The derivative of 3z squared with respect to x will be 0 because we treat z as a constant. And the derivative of 4xy with respect to x, 4 and y are both constants, so our derivative is just plus 4y. And then we just walk through and calculate f sub z, the partial derivative of our function big F with respect to z. So the derivative of x squared y squared with respect to z is 0 because both x and y are held constant when we take a derivative with respect to z. Here I'm going to get minus x squared is just a constant, and that 2 on the z squared is going to come down into a coefficient position. So I'm going to get 2x squared z, and then I'll look at this term, 3z squared is going to give me a plus 6z, and the derivative of 4xy is 0 with respect to z, and the derivative of minus 10 is 0 with respect to z. And now I can calculate my partial z partial x is just equal to the opposite of the f sub x term in the numerator, so 2x y squared minus 2x z squared plus 4y divided by my f sub z in the denominator minus 2x squared z plus 6z. And I probably should clean this up a little bit. I can see that a 2 can factor out of the numerator and denominator, and I probably should just go ahead and distribute the minus sign into the numerator. So if I factor a 2 out of the numerator and denominator, that will cancel, and then distribute the minus sign in. So I'm going to get partial z partial x equals minus 2, I factored the 2 out and cancel it with the 2 factored out from the bottom. So it's just going to be minus xy squared plus minus plus x z squared minus plus will give me minus y over, and I factored a 2 out. Actually, it's going to be 2y. I only factored a 2 out of the numerator. So factor 2 off of this, a 2 off of this, a 2 off of this is going to give me a 2 times y there. and factoring that 2 out in the denominator is going to leave me with minus x squared z plus 3z. And usually you're going to manipulate it so that you don't have a minus sign on the front if you can. So I would probably pull this and write it as x z squared minus my xy squared minus my 2y. And then down here, probably put that 3z first minus the x squared z term. And there's my partial derivative with respect to x using the formulas we developed in video, what was that, video 4. So you can see it's a pretty nifty way to do it. Conceptually very pleasing, I think. You might not agree, but I like it.